areas, and it's a really difficult. It's really a difficult topic. In Norway at the moment, there is nearly 100,000 people living on quickly, and there are more than 3,000 zones registered where we have a high danger area for quickly landslides. If we go back in history, there's been more than 1,000 persons that have lost their life because of quickly landslide in Norway. So this is a really an important type of natural hazards. Uh, Sensitive clays occur in many countries of the world, so it's not just for Norway. This is something that we have in many countries in Russia. But today, the focus of my presentation will be on Norwegian conditions. I'll give a little background about what quick clay is, some of the methods that we use in practice to detect quick clay, for example, some examples of geophysical methods, in situ methods that we use, and also in terms of slope stability assessment, how do we characterize the soil? What type? How do we define our design parameters? And also looking, this is more on the failure behavior when we're looking at stability assessment. But then we also have to look into the post-failure behavior. We're talking about runout and retrogression of these large landslides. So this is a bit the scope of my presentation today. Let's see. Oops, sorry. So what is quick clay? Well, quick clay, this is it's a marine clay. It's a clay that was deposited in the marine environment for many thousand years ago. And because of the geological history in the northern hemisphere, because of the glacial rebound following the melting of the glaciers, there was a relative fall of the sea level. So these clays that were deposited in the marine environment today lie in above the sea level, and they are affected, if you want, by groundwater by fresh groundwater flow. And this flow of water is leaching the salts that were initially between the clay particles. So, and this is sort of affecting the electrochemical bonds between these particles and renders the structure metastable. Uh, as a definition in Norway, what we say a clay is it's a clay that has a remolded shear strength, the CUR here, that is lower than 0.5 kPa. Uh, and my present, this is not working, but okay. But this is a different, this can be a different, they use different boundary for the definition of quick clays. In Sweden, for example, they use 0.4 kPa, while if you go to Canada, they don't use the term quick clay. They will use sensitive clays with different scale of sensitivity. So this is an important difference. Now, some ways to produce quick clay through geological history is that either it comes from precipitation, so on the top of the soil, or it can be from groundwater flow going from through fissures in the bedrock and then in the material, for example. So over the years in Norway, there have been many quite destructive landslides, and these are just a few examples of recent landslides since 2009 in Norway that have affected people and led to loss of life. Yesterday, there was a report that was made publicly available following one of the largest or most deadly quickly landslide of recent history. That was the landslide at Gjerdrum that occurred on New Year's Eve this year. There were 10 casualties from this landslide, and you can see the scale of it. There was several houses that were taken by the landslide on New Year's Eve, and it was a national catastrophe. So yesterday, there was an expert group that have been working on this landslide for the last year now, and they could point out that the cause of this landslide was actually erosion in a river, a creek that had not been completely secured over time. But one thing that we see is that if we go back the last 20 years in Norway, most of these quickly landslides are actually triggered by human activity. And it is nearly 85% of the landslide triggered by human activity. And there are several, one at Statland that was triggered by vibro compaction along the shoreline. The one here at Lyngen, it was a small embankment field along the coast that triggered a landslide, and it retrogressed on land. The one Leksvik here, same thing. It was a small quay that was being built along the shoreline, while the one here at Tosbotn in 2016 is a bit different. It was leakage from a hydropower tunnel that was being filled up, and then it was hydraulic fracturing of the rock, and then leakage that the water went into the soil and triggered the landslide. So there's all kind of different triggering mechanisms here. But what it shows us is that there's always more to learn about sensitive clays. And even though we are coming very far today with our knowledge of this and our methods to collect information, there's still quite a lot to learn. This is just a graphic in Norway since the 1970s. Some of you may have heard about the Rissa landslide back in 1978, and that was an important landslide also with loss of life and very large damages. This landslide led to the population being more aware of this type of material and also for the authorities. And it led to the start of a national program for mapping of risk associated to large quickly landslide in Norway. The immediate consequence of this was that following the start of this mapping program, and due to the awareness of the population and the authorities, we can see an important decrease in the frequency of landslide per year. And this is very good to see that as engineers, when we do maps, hazard maps, and we learn more about these materials, then we are in a safer environment. What we see, however, is that lately, the last 10 years, there's been an increased frequency again in these landslides. And a lot of people are talking about climate change and so on, but quickly landslides are not really affected by climate change. Many of them are triggered by human activity. And actually, it's more sort of a political effect here. It's more political change that are really changing the frequency of landslide here. There was a financial crisis in 2008, and that led to the government putting more money into the construction of railways, road infrastructure, and so on. Large investment in the public transport and many projects. And then when things go too fast, then you have a higher frequency of landslides. So again, it shows that the work we are doing as geotechnical engineers is very important. So the question is, how will that be during the next decade? There are many methods today to identify quick clays. Quite often in our project, we start through geophysical methods because that gives us a really nice overview of the soils that we have, and it's easier for us to go and then put some soundings or boreholes to correctly identify quick clays. One of the methods that is very used these days in Scandinavia and also in North America for delineating quick clays is the use of electrical resistivity tomography, so ERT method. The ERT doesn't tell us where quick clay is, but it tells us where you can have leach clay. There's a large difference in resistivity between a leach clay and a non-leach clay, because the leach clay has no salt in it anymore, while the marine clay that is non-leach still has salt. And you can see the blue color is for marine clay, while the leach clay is more a greenish color, and the resistivity will vary between 10 to 100 ohms meter. And we have really good experience with this method. Nowadays, for large infrastructure project, like when we want to uh, uh, construct several kilometers of highway development or railways for that sake, we can also use airborne electromagnetics. So it's a bit of the same as electrical resistive tomography, but it's through helicopter. It's a bit coarser, but still it gives you a very good overview of the resistivity of the material, the depth to bedrock, and it's been nice to use in order to precisely a place where we need some more information from boreholes. So this has saved us quite a lot of money in many projects lately. Uh, if you want to really find also find where we have quick lays, we need to have soundings and even take some samples, because as I mentioned in the beginning, the definition of a quick clay is a mechanical definition. It is a clay with a remolded strength that is less than 0.5 kPa. But we still try to use, for example, CPTU to find delineate sensitive clays, and also in Norway we have some soundings methods. One is called the rotary pressure sounding methods, and it works really well to delineate quick clay. When we look at CPT data, for example, so it will be these first year. This is results from our national test field on sensitive clay close to Trondheim, here where I live. So we have the standard results with the corrected tip resistance, the sleeve friction, the pore pressure while penetrating the soil. And then we have a pore pressure parameter BQ here. And also on our CPT, we have a resistivity probe to see to measure the resistivity in the soil. What we see in sensitive clay is that there's a high pore pressure while we are pressing down the sounding, and usually the BQ parameter is higher than zero 0.8 in quick clay. For the rotary pressure sounding, this is a really rough sounding method. It rotates while it goes down in the ground, and it can go through both gravels and stiffer material. But when it gets into very sensitive clay, there's a tendency for a lower force there. If it's constant or it goes lower, then we know it's a material that is sensitive and there's a low remolded strength. So we use this one as well to check where there's a possibility of quick clay. So in our projects, when we have defined and map where quick clay can be, the next part usually is to try to define the design parameters for slope stability assessment. And the Norwegian procedure for that is quite simple. There's different ways we can do that. If we focus on the strength properties, quite a lot of our slopes are susceptible to undrained failure, meaning that it's the short-term loading that can render the slope unstable. That can be due to rapid erosion or an embankment fail, or, for example, blasting in the surroundings or things like that. And usually what we trust the most in Norway is to do triaxial test on high quality clay sample in order to get the undrained shear strength of these clays to use directly in our analysis. But sometimes we don't have access to high quality samples. So what we use would be CPTU data. And then through empirical correlations based on high quality samples in the surroundings, we would use the CPT data in order to get a shear strength profile. If we don't have that, maybe early in a project, what we can use is quite often we use a Shansep approach. So meaning that we look at the stress history in the area, and with empirical factors, try to perform a shear strength profile for the soil. And maybe the data that we use the less in for design profile would be Falcon test, uniaxial test, and even vein shear test, because vein shear test doesn't work really well for Norwegian clays. With clays of low plasticity, you have some progressive failure mechanisms along the vein that renders the measurements unvaluable. So a typical profile will look something like this, where in many cases, we have all of this data, but then we will make a design profile that is quite often based on the triaxial compression test, so the circles that you have there, and then also based on CPT as a second part, while results from uniaxial tests and Falcon tests we see quite often will fall below this. Uh, One important thing to remember in sensitive clays is that the quality and the reliability of the laboratory and field data can be significantly affected by sample disturbance. And then in turn, sample disturbance may affect key design parameters such as compressibility, pre-consolidation stress, and undrained shear strength. Here is an example, again, from one of our field tests that we have close to Trondheim, where we show the difference between a perfect high quality block samples in clay. So that's a sample that is 250 millimeter in diameter, compared to more standard samples that are taken into consulting projects. So that would be a 72 millimeter piston sample. So this is a plot of an odometer test, constant rate of strain. You have the constraint modulus here with the effective stress. And what we can see is that the yield stress, or the pre-consolidation stress, is much easier to assess from high quality samples than lower quality samples. Also, we see that the constraint modulus for low quality samples will be lower before or near the pre-consolidation stress, and higher than in the normally consulted zone. So that could be non-conservative in many engineering problems. So it's important to be aware of that. Same thing if we look at strength results from a triaxial test. Here we have a and we perform tests based on block samples, both large block and mini block. The mini blocks are 150 millimeters in diameter, and then compared to poor quality piston samples. And you can clearly see the difference. There's a peak strength at nearly 1%. This is typical for very sensitive brittle clays, where you have failure around 1%. But then the difference in strength here is quite important. We have a difference in peak strength that is nearly 45% difference. Uh, and the interesting thing here is that when you look at, there are different criterias that exist in the literature to look at sample quality. All of these samples here are in the best quality, quality one, if you look at the parameters by Tom Rune and my colleague that published for many years ago. So it doesn't mean that if you have a high quality, you have perfect samples. So this is important to take into consideration. And there's quite a lot of work going on at the moment also in Norway to look into better criteria to really quantify the quality of samples. Another really important thing when we look into slope stability assessment for Norwegian clays is that these clays are are anisotropic. It means that they will behave differently depending on a number of factors. It can be rate of loading, stress path, stress orientation, also the volume of the material in the lab. So it means that the strength you have from a triaxial test will be different than the strength you have from a direct simple shear test. It will be different than the strength you measure in the field, and so on. And what we know that for Norwegian clays, usually standard number here is that the anisotropy factor between extension and compression is around 0.63. And then between direct simple shear and compression is approximately 0.35. And these are for low plasticity clay. So it's a bit different if you have higher plasticity in our case. But these are factors that we also take as input in our stability calculations. Uh, This here is an example again from our research site, just showing these different numbers here, where the undrained shear strength in compression is larger than the one in direct simple shear, and again larger than the one in extension. For this case here, we have the undrained shear strength on one axis with depth, and at our research site, we have very sensitive clays from approximately 7-8 meters below the terrain. So what we see here is that the triaxial test on block samples is much higher than the one on simple shear, these circles here, and again higher than what we see in extension, which are these boxes there. And then fall count are quite often much below that. Once we have our design parameters, design factors that we use in Norway are quite simple. The safety margins that we use usually are looks something like this, where we are looking into increasing the safety of a standing slope. So what we use is that depending on the consequences of a given project, so it will be a different if we have, are you building an hospital or building just a garage for your house. For an hospital, you would need significant improvement, while for a small house, you would need solely an improvement. But what we do is that we're trying to get a safety of factor of 1.4. If you don't have that, we are looking for an improvement. So if you have a safety factor of 1.2 for your given slope and you want to build an hospital, for example, you'll have to go to this line here and you need a significant improvement that is around 7%. And we use that because we know that this improvement is real. It's a sort of Bayesian updating. And this is the way it is done in Norway. So once stability assessment have been done, usually what we look at is the next stage. Pictures I showed earlier that some of the devastating factors of quickly landslide is the retrogression potential that it has, and also the runout distance that can be quite important. Uh, there are no very good methods for this at the moment, and these are things that we're working quite a lot with. When we're talking about retrogression, we're talking about this distance from the toe of the slope and going back. Where will it stop? And for the runout distance, it will be from the toe and then downstream. Usually, what we do is that we first of all we try to analyze what type of landslide would this slope be subjected to. Will it be a retrogressive landslide, flake type landslide, or simply a rotational landslide? And we came up with some criteria recently in order to delineate these types of landslide. We see that based on all the data that we have in our database, retrogressive landslide is around 1 kPa. And then when you also have more than 40% of quicklay on top above a critical failure line. And then we do similar for flake, and for rotational landslide. Usually, the remolded strength is above 1 kPa. When it comes to the estimation of the distance of retrogression, we can base that either on sampling and soundings that are in the surroundings, and by looking at the bedrock thresholds and the topography. And if this is not possible, then what we do is, again, through empirical methods, we will draw a line that is 1 to 15, a slope. And then when we get out of the quicklay, then we draw a 45 degree angle, and this would be the based on empirical data, and we 90% of our landslide would be into this these methods. And then the last part will be to evaluate the runout distance. And again, what we use mostly at the moment is looking into empirical approach. And there's a direct relationship between the retrogression distance and the runout distance. This is based on historical data that we have. And it really depends on what type of terrain you have in front of your landslide. Is it a channel? Will the landslide be channelized, or is it open landscape? So this has also something to do with how far it will go. But lately, we've been also looking into numerical modelings, what type of methods could be used in order to model the runout distance of landslides. The problem is that most of these tools that are available on the market, they are meant for debris flows, they are meant for other type of landslide, and do not really reflect really the behavior of quicklay landslide, where really the material behaves like a soup and really a liquid behavior. So it's really difficult to use these models because we have to tweak always the parameters, and it's really difficult. But lately, what we have done is that we have uh, started uh, a new viscoplastic model with the Archibald-Clay rheology. And I don't know why this model is not working at the moment, but it was supposed to show the model here. But okay, I'm sorry. But this is working very nice at the moment. And we recently have a paper in in computers and geotechniques where this model is well described by my colleague Songkyang Liu. So this is something you can have a look at. So there was a short presentation that we have with associated with sensitive in quick clays in Norway. This is a very challenging material to work with for many geotechnical engineers. And if we can summarize, maybe the challenges are associated with first the detection of these clays, also the sample quality and the assessment of the geotechnical properties. This goes together. And something that we are working quite a lot with at the moment is to into the hazard assessment and how to relate to the retrogression and the runout behavior of these slides. So thank you very much for your attention, and I have some time for questions if you have any questions. Thank you
Thank
very
you very
much.
much, Jean Sebastian. My co-chairs, would you like to add something, please?
Uh, I just would like to thank you very much for this very nice lecture. And I have two questions. One question that I saw that somehow that these layers are thick generally and not thin. So my question is that in Norway, these quick layers are occurring in general in a thick formation, so several meter thickness, or sometimes it may occur as a very thin layer. And the second question that I heard that it was mentioned that there are some debris flow data. And my question is that in the future, we may have some information about this debris flow also, because we are interested in the grading curves of this kind of materials. And for example, in tomorrow's grading curve workshop, it could have some interest. But of course, we won't have very soon, but in some stage, may I ask some data in connection of debris flow also? So these
Hmm.
are my two questions.
I can answer the first one regarding the thickness of these soils. It really depends on where you are and the topography and the surroundings and the sites. But usually, quickly will start from maybe 2 3 meters below the terrain and can be 10 20 meters in thickness. But I've seen it also that these clays can be very thick if they are produced by groundwater flow coming on from the bedrock. So it really varies. We can have some thinner layers, but this is quite often not so important. So we focus on more thicker layers. But it's true that they may be several meters in thickness. Another aspect that I didn't mention is that we also find these clays out in the fjords because of the groundwater flow going from land towards the fjords. These clays can be leached up to 100, 200 meters out in the salt water. So this is also something that is maybe very strange for people, but there is fresh groundwater flow in the seabed of these fjords. So this is important to take into consideration if you want to build structures there. For the grading curves, sure, just take contact and we can always send some data that we have.
Oh, thank you very much. I am very happy with this. So thank you so much in advance. And I will write an email in connection to this. Thank you.
You're welcome.
Any other question? Probably there is no other question now. So I give back the word to DNS. So probably he may